problem 30 in section 1.1. There has two parts. The function f is continuous, p is some point in between. The first part says that if f of p is not 0, then there exists delta such that f of x is not equal to 0 in the neighborhood of p with radius delta. So that's the first part. The second part says that if f of p indeed is 0, then there exists there's some k greater than 0, arbitrary k greater than 0, then there must be some delta, which depends on the k, such that f of x is less than or equal to k for any point x nearby the point p. So this is actually a very straightforward result because of the continuity of f. For example, for the first part, if you have p here, and your f of p is not 0, that means your f of p is either above or below this line. Right? So let's say that f of p is positive. So by continuity, you know that you will be always positive nearby this p, right? Because it's continuous. How do we prove this rigorously? So if you have done, I guess some of you have done this in calculus, because this is actually a very important part of calculus to show the to study the continuity of a function. So let's see how do we do this here. Again, as I said, without loss of generality, we're going to assume that f of p is greater than 0. If it's less than 0, it's just the same argument. So what I'm going to do is that we're going to set epsilon to be this value to be half of that. So that means we're going to have this as our epsilon. Both of them are epsilon. Okay. So now you know that because this is continuity and I chose this epsilon, then there must be an interval here with the radius delta. So it's going to be p delta minus delta, p minus delta, and p plus delta. And over this interval, the function is taking value in this band, which means it's between the distance between the value and the f of p is going to be less than epsilon. So that means the function is going to be taking value in this band right here. Okay, so and then you can apparently they're above 0, right? They're actually above this line. Okay, so formally speaking, here when epsilon is set to this way, we know by continuity of function f at point p, it's actually continuous at every point, so it must be continuous at the point p. There exists a delta that depends on the epsilon, such that the f of x minus f of p is less than delta, is less than epsilon, where epsilon is equal to this. So for any point x in the neighborhood of p, this will be less than half of f of p, which is a fixed number. Now you can remove the absolute value. You know that this just means that this thing here is less than that, but on the other side is greater than negative 1 over 1/2 of f of p. Okay, and then you just move f of p to this side. You have cancellations. You have a half of f of p left. So this is actually greater than that. And the half of fp we know is greater than 0. So we can choose the epsilon to be half of fp, or like 1/3 of fp, 1/10 of fp. It's really up to you. As long as the you get a very narrow bound here that is totally above 0, that'll be fine. Okay, so that's the first part. The second part is even more straightforward because it's just the definition of continuity, right? If you choose epsilon to be k, as said here, then you know that for any there exists a delta that depends on this k, such that the distance between f of x and f of p will be less than k when the x is in this neighborhood of p. But no, look at here, because f of p is equal to 0, so it's just gone, right? So it's just f of x less than k, as you want it here.